This session is to give the award for the 2025 Tucker-Hasegawa Award. I'll give you a bit of short introduction about the award, if this works. Here you go. So this is taken from actually the document that talks about the award on our website. The Tucker-Hasegawa Award is actually the most prestigious award that we give at IARC. It recognizes individuals in industry or academia who have made major, distinguished, and sustained contributions to the field of automation and robotics in construction. The name Tucker-Hasegawa, for those who haven't been in the organization for a long time, refer to the two professors from Japan and from the United States who actually created IARC a long time ago. I don't remember, 1984, something like this. So a really long time ago. We're very fortunate to have had a long-lasting and high-impact organization. Thanks to them. These are the previous recipients or awardees of the Tucker-Hasegawa Award, and you can see it was started in 1999. So today we will be awarding the 26th Tucker-Hasegawa Award, and the people on that list have really made strong contributions in their field of research or education impact. But also to IARC, right? There's a broad range of criteria that we take into account every year. How do we decide who gets the Tucker-Hasegawa Award? Well, we have a committee that we set up every year. This year, I asked actually our colleague from Tsinghua University, Professor Nan Li, to chair a committee that included Professor Marcus Koenig, who I know is in the room as well, Professor Kwon, Professor Eng, and Professor Zhenyu Zhu, and myself. Every year we make a call for nominations around November. Anybody in the organization is welcome to submit a nomination. Okay, we try to be as open as possible. We welcome nominations. This year, we actually got 5 nominations, which was actually probably the largest number of nominations we had for a number of years I've been involved in doing this. And this is really good because it gives hard work for the committee, and it gives us really good options and opportunities, and it really shows that there's great contributions that people have made to our community. The criteria, as mentioned, are research contributions, education contributions, service contributions, and overall impact. And some people are, more in one area, more in another, but we do take everything into account, and we try to identify who we think is most deserving to get the award every given year. Now, let me tell you who the awardee is this year. I have to say, first of all, that we evaluated the 5 nominations, and we didn't end up having we had a good discussion in the committee, but we had a unanimous decision ultimately, okay? And I'm very pleased this year to award the Tucker-Hasegawa Award to a great colleague, Professor Vinnet Kamat. Congratulations, Vinnet. We are all really pleased that you received this award this year. You have done so much. The award actually states that the reason why you get this is for your distinguished contributions in the field of automation, in particular, your extensive research on human-robot interaction and adaptive core robotized construction, and I think this is also very important, your unwavering contributions to our research community in IARC and beyond IARC, not just IARC. So please, Vinnet, come on in. We have a lovely award for you. We'll take a couple of pictures. Youngwon, you want to come along with the president, please? And then. Congratulations. So what we have now is we'll leave the floor to Vinnet a little bit to give us a presentation, reflection of his work, etc. on this. And I have everything for you.
Thank you. Thank you, Fred, for the very generous introduction. And thank you all for being here. It's one of my life's utmost honor to be the recipient of this award this year from an organization that I've been familiar with and involved with ever since I was a grad student more than 25 years ago. So I'll try to keep this talk short to the amount of time we have available here. And instead of talking in depth about a particular research project or something like that, talk a little bit about how I got into research in construction automation and robotics, what the landscape looked at that time, what has changed, what has not changed, and along the way, as we learned, each new insight through a different study, the work of a different PhD student, how that eventually led to us internally developing like a roadmap for research in construction automation and robotics within our own lab, and to some extent then for the use of others in the community as well. So hopefully I'll leave some time for questions as well. So I'll start with that historical perspective on robotics in construction work. What inspired us to start working in this area? The challenges for robotics in on-site construction work as they existed then and as they still, many of them are present today. Our research roadmap, like I talked about, one example of co-robotic construction work, since that was part of the reason I was recognized with this award, one example of co-robotic construction work and the project workflow it enables, and some concluding remarks. So I'll begin quickly with a historical perspective on robotics and construction work. Generally speaking, over time, we feel that there are some systematic barriers to innovation in general in the construction industry, and many of them apply directly to construction automation and robotics, or the proliferation of robots in the construction industry. Now, many of you have international perspectives. Many of you come from countries in Asia, Japan, and others, where robotics is much more proliferated than in the US or North American context. So I would interpret this primarily from our perspective, the North American perspective, and acknowledge at the same time that other places are still very advanced compared to where we are. So the basic premise is, on-site construction work to this day remains what we call the 3D: dull, dirty, and dangerous, right? And the industry, when we started and as of today, faces severe skilled labor shortages. So if you talk with any contractor, that is the main reason they would even hear anything about construction robots or introducing robots on construction sites. One thing that is often not discussed in a conference like this is the contractual arrangement of how a project is procured, right? And mainly the fact that the construction industry is very highly fragmented. So it's not like one company. Again, unlike countries like, say, Japan, Kajima, Shimizu, with exceptions like that, there is not one company that directly sources an entire building or an entire project. There are many different contractors, subcontractors, and many different stakeholders. So you don't really know where the responsibility lies as far as innovation is concerned. Because of the contractual method, the industry is very conservative and risk averse, right? So once a technology is proven, everybody wants to be part of it. And historically, this has happened with scheduling and CPM, more recently with BIM. And now everybody wants to say that they are into automation and robotics and digital twins. But to what extent they are really differs, and is a matter of perspective. So this also leads to a lot of inertia and resistance to change the contractual methods. And if you don't believe me that there is inertia in the industry, I'd like to share a few slides courtesy of my colleague Cam Saidi at NIST. Most of us have seen this picture as a poster somewhere, right? But if you see this picture, could be a building in Montreal right now, right? So it's not much has changed into how construction is procured. This is how a crane is signaled maybe decades ago, a century ago, And this is still today how you would see a crane moving around on a construction site. This is how concrete was placed for a dam a century ago, and very likely the site we are going to tomorrow as a group has similar type of construction that put that dam into place. So things haven't changed much on the construction front. In many cases, even though we see a lot of energy now into startups who are trying to introduce automation and robotics, particularly in on-site construction work. So with this backdrop, our main context in beginning work in this direction was many people asked in manufacturing, productivity is high, safety has gone up, partly in reason due to robotics. Why not in construction, right? What prevents robots from proliferating in field construction work in particular? So over time, we developed our own picture as to why this is exactly the case. And I'll summarize maybe like 10 or 15 years of understanding in one or two slides over here. The main reason is that a factory setting like this, a typical manufacturing environment, is a very controlled place where the metrology or the ability to locate a robot at sub-millimeter level is practical and possible. And more importantly, the work done is organized in a paradigm called process interaction, which means the robots and or the workers stay where they are, and the work in process inventory comes to you. You add value, and the inventory moves forward. Compare that to a construction site, other than what some might construe as visible chaos on the site. Not every construction site is chaos. People know exactly where things are. But the key point that differs in organizing construction work compared to manufacturing is a paradigm called activity cycles, which many of you will be familiar with. The notion that for construction, on-site construction work, the work doesn't come to you. The resources, the people, machines, tools, components have to go to the place of work each time they add some value in that environment. So with this basic understanding, there are some key differences that serve up as challenges for robotics. Every project is unique, we know that. But many people say the construction work is repetitive. So we pondered over this quite a bit. And in the work of one of our recent PhD students, we defined this term quasi-repetitive, where, yes, repetitive, you are going through the same motions, but no two instances of the work are exactly alike, right? So maybe a crew will install hundreds of windows or hundreds of doors, and that could potentially be robotized or co-robotized, but no two instances of that window are going in the exact same place in the frame. The location is changing, the geometry is changing, the floor is changing, the rough carpentry around it is changing. So each circumstance is different. So quasi-repetitiveness creates a lot of challenges. The environment itself, like we saw in the picture, is at best rugged, cluttered, and constantly moving, right? So we call this an unstructured environment, particularly in the context of robotic construction work. In terms of tolerances, things in a factory are often at a sub-millimeter level precision, but on construction sites, even in a modern building like this, if you really look with a fine-toothed comb, you'll realize that not everything is exactly where the BIM says it was, right? Oftentimes it could be a few inches apart, and none of us care because the form and function generally look the same. But from a robotics perspective, it matters quite a bit as to how do you make it add value with this level of tolerance stack-ups. As I mentioned, because of activity cycling, the crew, equipment, materials need mobility, and mobility is a very big challenge in high precision robotic work. And last but not least, related to the mobility is the fact that each time a robot moves, you have to set up a high precision metrology, a way to let the robot know where it is in relative to the construction site around it. So these are some key challenges that we have identified over time as being the key sort of impediments to wide proliferation of robotics in construction work. So based on this, I'll give you a quick introduction to sort of how this evolved into a research roadmap for us over the course of the work of several PhD students. The basic basic premise is that any mobile autonomous robot can have three functions, right? The ability to sense an environment, the ability to think or reason about what to do next, and the ability to physically perform that action. So we call that sense, think, and act. Probably figure one in most robotics textbooks. Many years ago, in one of the IARC's publications, I don't remember the exact name, I had seen this idea being broken down into a three-axis diagram, right? Where one axis says planning, the other axis says cognition, and the third axis says physical, where the notion is any piece of construction work, you have to plan how you're going to do it, including any improvisation when things don't go per plan. You have to be cognizant or aware of what is in front of you and make decisions on the fly, right? As a human, we do this interactively without making it a formal process. And finally, once the two come together, you're going to actually do the physical work. So if a human does all these three aspects, planning, cognition, and physical, then you're talking about manual labor. But now let's say the human does planning and cognition, but the physical part is done by a machine, then you can think of it as a typical construction equipment, right? Like a bulldozer or an excavator or something like that. You can also think of it as a teleoperated robot because you're doing the planning and cognition as a human and commanding the physical work of a robot. So given all of these challenges that we identified earlier, our main focus shifted into to make robots possibly more proliferated or practical in terms of adding value on construction site. Can we move their abilities along these two other axes, the planning and the cognition? And as it turns out, planning and improvisation, even today with all AI and other types of things, still remains the domain at which humans excel much better than an AI agent or a robot. So our first low-hanging fruit was, can we make robots have more cognitive abilities, the ability to interpret a workspace in the environment and add value and make it smarter to do that kind of work? So the first piece of work was done by our PhD student, Kurt Lundin, who is identified here as the first author on this paper. So once we had success in this work, we began to realize that what the human can do and what the robot can do and what each entity or agent is best qualified to do in a piece of construction work lies on a spectrum. It is not just one point of distributing responsibility. And that spectrum eventually led to this research roadmap, which we also called like the ladder of human-robot collaboration. And the chief architect of this was my PhD student, Polar Liang, who is sitting here at the back of the room and is the first author on this paper. So the idea here is that the first rung of the ladder, the pre-programming, you can replace that with teleoperation or a piece of construction equipment, right? So the human is doing the planning and the cognition, the machine is doing the physical work. But as you start climbing up this ladder, the robot is doing more and more of the cognition with all the way to full autonomy, where the robot is doing planning, cognition, and the physical work. I should say upfront that the top rung, full autonomy, is just a theoretical concept. And I think it will remain like that for a long time, at least the way construction is today. But we, just for academic completeness, we have it staged like this. So over the years, we kept on working along these rungs of the ladder. As I mentioned, the next work, which was done by Polar Liang here, focused on this concept called imitation learning, where we tried to explore whether we can make a robot learn how to do construction work by looking at other workers doing it. And then with time, that was further expanded by a few other PhD students, including Somin Park, who is here, where they introduced the ability to have a construction robot in a process level digital human in the loop digital twin, where human and robot can work together to improvise and the human can supervise the robot to add some value to construction work. So that's how we progressed in this work. So I'll just give you an example of how all of that came together in one particular study. And before that, I'll just introduce briefly our lab environment at the University of Michigan. One of the things we have always tried to do, even though it has been extremely hard to bridge this gap, is work with full-scale physical robots, because many times the gap between having a successful algorithm run in ROS or Gazebo or in any other kind of simulation, and then to make it work on a real robot, that so-called ditch of death is very, very wide. So you never know what you'll come across when you're going, trying to bridge that gap, because simulation and reality, there's a lot of difference, particularly at full scale robots like this. Even in departments such as computer science or robotics, many state of the art algorithms are tested at a smaller scale with tabletop robots and so on. But in construction, I think it's very important that we test things at the full scale like this. So one of the things that we have worked on is to recreate this notion of how human workers learn from other human workers, right? So there is this notion called master apprentice. So even in today's context, let's say in the US, I'm assuming Canada and other parts will be similar. A novice worker first goes to trade school. He or she learns the basics of electrical, plumbing, fitting, what have you. Then they are paired with master craft worker who is working in the field, become their apprentice. And over time, they observe the master craft worker, learn more and more from them, get more and more responsibilities, eventually graduate to becoming a journeyman, it's called in the US, to becoming an independent craft worker themselves, right? So could we recreate that kind of a learning mechanism between human robot teams? And as step one, what would be needed for a robot to observe a human doing this kind of work and be able to repeat it in a different place, different context, different setting? So that was the basic premise of this work. And over time, we have experimented with many different things to replicate how humans work. So I'm sure all of you have some experience. Something is broken in your house, and you look at some YouTube videos, look at some IKEA videos, and try to fix it. So our one line of inquiry was, can a robot observe some construction videos and just learn from those whether they can get some state spaces of how to do construction work? The second, of course, was actual human demonstrations. And these still remain the key, even though it defeats the purpose of a human having to show repeated tasks over and over again. And now with few shot learning and things like that, it's much better. But the idea of a human having to show several hundred repetitions was a little bit daunting at the time. But one advantage that gives is when a human demonstrates work, they can also demonstrate the use of force, right? So as an example, with this particular task here, handling ceiling tiles, if a robot grabs it by full force, it's going to crush the tile, right? So it is important for the robot to understand not only the kinematic space that is involved in installing such a tile, but also dynamically what forces are involved and how delicately or how strongly to handle such an object. So we can train a robot through those data streams as well. And another PhD student, Hongri Yu, who is now at Virginia Tech, she did some work in this regard in particular. Similarly, we also developed the ability for a human to demonstrate in VR rather than in the physical world, because arguably demonstrating in VR is much less physically strenuous than in the physical world itself. And once the human demonstrates in VR, then there is the ability to parameterize it and create several different combinations in VR without the human having to necessarily move the joysticks and the other controllers and things like that. Following this, or in parallel with this, we also developed a way to organize or break down construction work into low-level tasks or subtasks, right? So those of you who may have studied work or the performance of work deeper than we have, you know that you can break down work all the way to elemental motion, and then you get into which of muscle fibers and so on. So there is sufficient depth at which you can study the breakdown of work. For us, we were only interested in like the elemental motions, meaning what is the lowest level elemental motion that can be taken as a building block. And with those building blocks, you can concatenate or chain them together to create any kind of construction task. So break that down into, so that way any observed task can be broken down into a chain of observations, and it gets stored in the cloud using this hierarchical taxonomy. Once stored in the cloud, other sites, other locations, other robots, other agents can access this information and adapt it to a different geometry in a different place as well. And last but not least, this I think was fun part for Somin, who did this work, is when two humans, master apprentice, talk to each other, they have a certain parlance or cadence with which they exchange information or give instructions. I might say to you, can you pick up that hammer and install this panel over there? I may do something like this. I may not necessarily say, go to the BIM and element XYZ, take this and put it on stud, something. I may not say like that. I may talk more naturally. So you want the robot instructions to be computer interpretable by reference to elements in the BIM, locations in the environment, but you also want the ability to tell the robot, pick up this panel and install it on the first stud over there. So if you give these types of instructions, the interaction becomes much smoother. And Somin did quite a bit of work in that regard as well. So all of these things came together in, like I mentioned, like an AI-powered core robotic workflow that basically not only lets robots learn by observation, but it also lets a human be part of a process-level digital twin where the robot knows what it is supposed to do next. It can show the human worker what its plan is. The human can help it improvise, and then the robot proceeds to do what is next. So it becomes like a true human-robot partnership with these four elements, like real-time digital twin, hierarchical imitation learning, like I explained, natural language and VR interfaces. And all of this is possible because very early on, we developed the ability to position and orient robots very accurately using computer vision methods so that there is a mobile, rapidly deployable metrology. And that work was done by my first student in robotics, Chen Feng, who also happens to be this conference's best paper awardee. So, all right. So this is just side-by-side picture of how all of this comes together. I may not play all of it now, but what we have here is on the right, a digital twin that is like a sub-millisecond representation of what happens in the real world as well. As clearly the real world robot moves, it is represented in the virtual world as well. But what is important as a feature in this environment is there is interactivity between the human and the robot. And once the human declares their intent or instruction for the robot will first make a plan, demonstrate it in the virtual environment. And only when the human is happy at what is going to happen next, they will give the robot a green instruction to perform it in the real world. So now the robot, the blue one is a virtual robot, is demonstrating what its plan is in the real environment. And this work was primarily done by another of our PhD students, Shi Wang, who is at Texas A&M University right now. So in the interest of time, I won't play it all and move on to just make a few concluding remarks and take some questions. So in all of this work, we believe that, in today's construction site environment, the way construction is today, robots cannot really fully replace construction workers unless, the type of construction changes dramatically, becomes heavily prefabricated and interlocking, where you can make things off-site and, come on-site and just assemble them together. But robots do have the potential of serving as very useful assistants and partners to workers. And as a research community, not only should it be our goal to develop newer concepts, newer algorithms, but also try to identify an industry where there is value to be added, what type of tasks are best suited for automation, what results in improved profitability for our industrial partners, and so on. Talking about technicality, human workers are really good at planning, sequencing, improvising, and thinking of multiple things at the same time. robots are generally good at precise motion control and repetition without fatigue. So when we talk about the research framework I showed earlier, in any robotized or prospective robotized construction task, it should be thought about carefully what role you want the human workers to play, what role you want the robot to play, and give each agent what it is best at doing so that the task becomes a success. And historically, robots, when you think about robots, you think a teleoperated robot or a pre-programmed robot. And hopefully I give you some perspective on why this is challenging in on-site construction work. So historically, the challenge has been that human workers always wanted to retain all control except the physical part, right? But it is very difficult to teleoperate or pre-program a robot to do most construction work. So I think that's why the advances that are going on now in computing and more recently AI opens up new research avenues where co-robots can take on more responsibility, not only along the physical line, but also the cognitive line and maybe someday along the planning line as well. So with those comments, I'll just offer my acknowledgements first to IARC. It's really an incredible honor to be recognized with this award. Of course, our funding agency, the U.S. National Science Foundation, and our faculty collaborators and all the PhD students as well. So I thank you for your time.